Hello everyone, we will consider a problem from the Romanian Mathematics Olympiad in 1990. So we want to show that the nth root of the binomial coefficient 2n choose n is actually bounded for every integer n, and our goal is to find the smallest integer that bounds it from above. Okay, so we start with recalling the formula for the binomial coefficient n choose k. Remember that the formula is given by n factorial divided by k factorial n minus k factorial. And the binomial coefficient also appears as the coefficient of the term x to the n minus k, y to the k in the expansion of x plus y to the power n. So in other words, x plus y to the power n is given by this formula right here. It's n choose 0, x to the power n choose 1, x to the n minus 1, y. And the general term of this expression is n choose k, x to the n minus k, y to the power k. Since we are interested in the binomial coefficient 2n choose n, we will replace this n by 2n, and we obtain the following expansion. All right. So let's, one interesting thing here, what happens when we plug in x equals 1, y equals 1? So when x is equal to 1, y equals 1, we will get 2 here. So 2 to the power 2n will be 4 to the power n. And on the other hand, all these xy terms will be equal to 1. So we will just get the entire sum of the binomial coefficients equals 4 to the power n. All right, so for x equals 1, y equals 1, we get this entire sum equals 4 to the power n. Now the binomial coefficient 2n choose n actually appears in this sum, so it will be less than the entire sum, which is equal to 4 to the power n. So when we take the nth root right here, we will get 2n choose n to the power 1 over n. The nth root of it will be less than 4. So we already found an integer, which is 4, which bounds all these terms right here for all positive integers. And our goal, remember, is to find the smallest integer that will bound this 2n choose n to the power 1 over n from above. So at this point, since we are looking for the smallest positive integers, we have either a equals 1, 2, 3, or 4. So these are the integers that will bound this 2n choose n to the power 1 over n from above. Now let's compute a couple of terms. So remember the formula, n choose n equals n factorial divided by k factorial n minus k factorial. So when we plug in n equals 1, 2n choose n will be 2 choose 1, which is 2. This is greater or equal than 2 to the power 1. Okay. And this tells us that this cannot be strictly bounded. So the nth root of this, which will be here the first root, cannot be strictly bounded from above by 1 or 2. So therefore, in other words, a cannot be 1 or 2. So this leaves us with two choices. Either, since we know that the nth root is less than 4, so either the smallest integer that bounds it from above is 4 or it's 3. Okay? And we want to show that the smallest integer is not 3. So in other words, if we want to show that we can find an integer n such that 2n to the power n is greater or equal than 3 to the power n. So essentially, when we get the nth root here, when we take the nth root, 2n choose n to the power 1 over n will be greater or equal than 3, and that will rule out the a equals 3 case. So therefore, the answer in that case will be a equals 4. So we try a couple of numbers. So we can just, again, just using this formula, remember that n factorial is the product of all numbers from 1 up to n. So, and this is the computation for n equals 1. Now we can compute this expression for n equals 2, n equals 3, n equals 4, n equals 5, and we will see that for n equals 5, 2n choose n will be 10 choose 5, which will be 252, and this will be greater than 3 to the power 5. So essentially, we showed that this inequality right here, 2n choose n, will be greater or equal than 3 to the power n for some n. So therefore, 3 cannot be an upper bound for every n. And so a cannot be 3, so therefore a is equal to 4. So the smallest integer that bounds the nth root of 2 and choose n from above is a equals 4, and that's exactly what we wanted to find. All right, so thanks for watching.